Today we are going to discuss about the precise parameters of measurements. In our last lecture we have already discussed about the XRD diffractions and their applications. So, in this particular lecture first we will discuss about the different types of errors generally we are facing for doing the XRD. So, many applications of the X-ray diffraction require precise knowledge of the lattice parameters of the materials when we are doing the study. So, what are the examples? Like compositions of a given solid solutions, lattice parameter of solutions varies with the concentration of solid. And next, the thermal expansion coefficient by measurement of lattice parameter as a function of temperature in a high temperature camera or maybe the diffractometer. So, since a change in solid concentrations or temperature produce only a small change in lattice parameter, precise parameter measurements must be made in order to measure these quantities with accuracy. So, measurement of the Bragg angle. So, generally as we know that Bragg's angle is or maybe the Bragg's law is lambda is equal to 2d sin theta. So, precision in d or a depends on the precision in sin theta derived quantity and not on precision in theta, that is the measured quantity. So, the error in sin theta caused by a given error in theta decreases as the theta increases. So, in this particular figure you can see that at low angle that theta if we increase more, so automatically the sin theta will more than that, and at the higher angle is almost 90 degree, if we increase the theta more also, but sin theta change in the sin theta is very less. So, value of sin theta changes very slowly with theta in the neighborhood of 90 degree. So, when it is going near about 90 degree. So, a very accurate value of sin theta can be obtained from a measurement of theta which is itself not particularly precise provided that theta is near about 90 degree. So, by mathematical explanations also we can prove it. So, from Bragg's angle we know lambda is equal to 2d sin theta, differentiating the Bragg's law logarithmically. So, del d by d is equal to del lambda by lambda minus cot theta del theta. So, neglecting del lambda is del d by d is equal to minus cot theta del theta, and in the cubic system we already know that A is equal to d root over h square plus k square plus l square. In the cubic system as we know already A is equal to d into root over h square plus k square plus l square. Therefore, del A by A is equal to del d by d is equal to minus cot theta del theta. Since cot theta approaches 0 at 0 approaches to the 90 degree, and del A by A, the fractional error in A caused by a given error in theta also approaches 0 as theta approaches 90 degree or as 2 theta approaches 180 degree. So, what is the key to precision in parameter measurements? Use back reflected beam having 2 theta values as near to 180 degree as possible, and diffracted beams cannot be observed at 2 theta is equal to 180 degree. Therefore, the true value of A is found simply by plotting the measured values against 2 theta and extrapolating to 2 theta is equal to 180 degree. Then we are going to discuss about the diffractometers. So, the diffractometer is a complex apparatus and therefore subject to misalignment of its component parts. So, difficulty in most commercial diffractometers are like that, the impossibility of observing the same back reflected cone of radiations on both sides of the incident beam. So, there are several sources of systematic error in D due to the diffractometer. What are those? First one, misalignment of the instrument. Second is that use a flat specimen instead of a specimen curved to conform to the focusing circle. Third is the absorbance in the specimens. Fourth is the displacement of the specimen from the diffractometer axis, and the last one is the vertical divergence of the incident beam. So, these all errors has been listed in this particular image. So, first we are going to discuss about the misalignment of the instruments. So, the center of the incident beam must intersect the diffractometer axis and 0 degree positions of the detector slits. So, here the X-ray source, the incident beam is coming, then it is falling onto the specimens and then it should directly go to the detector itself through the detector slit. So, in this particular case the error may occur. Then flat specimen error, as I told already, the specimen surface should be flat, it should not be the curved one. Then there will be a error that is known as the flat specimen error. The entire surface of a flat specimen cannot lie on the focusing circle. What are the remedies? This error is minimized with loss of intensity by decreasing the irradiated width of the specimen by means of an incident beam of small horizontal divergence. So, in this particular case you can see that the flat specimen here the problem is that the error may occur in this particular case or maybe the zone. Next, third one is the absorptions in the specimen sample transparency error. While X-rays penetrate into the sample, depth of penetration depends on mass absorption coefficient of the sample and the incident angle of the X-ray beam. So, this produces errors because not all X-rays are diffracting from the same location in your sample. Yes, of course, because some reflection is taking place inside the sample, some reflection is taking place at the surface of the sample. This produces the error because not all X-rays are diffracting from the same location in your sample. That means it produces the peak position errors and the peak asymmetry, and also the greatest for organic and low absorbing or maybe the low atomic number samples. So, in this particular case, if you see, when the incident beam we are putting onto the sample from a lower angle, the area covering area is more, but when the incident beam angle is too high, then automatically the covering area is low, but penetration is more. So, what are the remedy? Specimens of low absorption should be made as thin as possible. Then number 4 is the sample displacement error. So, when the sample is not on the focusing circle, X-ray beam does not converge at the correct positions to the detector itself. Yes, because it can go to outside of the samples also, or maybe it can concentrate on a particular point also, it will not cover the area of the whole sample. So, the observed peak positions is incorrect. The largest single source of error in D given by del D by D is equal to minus capital D cos square theta by R sin theta, where capital R is the diffractometer radius, D is the specimen displacement parallel to the diffraction plane normal. It is positive when the displacement is in front of the axis itself. The next one is called the vertical divergence of the incident beam. The X-ray beam produced by the X-ray tube is the divergent one. The divergence means that instead of a single incident angle theta, the sample is actually illuminated by photons with a range of incident angles. Incident beam optics are used to limit the divergence. So, when the incident beam is coming, then we are using some divergence slits, so that the whole area can be covered. Then after that again we are using some kind of anti scatter slits, so that it can go through and then it can directly come to the receiving slit, it can fall to the single crystal monochromator, and then from there it can directly go to the detector itself. So, remedy: this error is minimized with loss of intensity by decreasing the vertical openings of the receiving slit. Divergence slits are also used to limit the divergence of the incident X-ray beam. Next, we can see some kind of errors because we are using cameras. So, due to that cameras also we can experience some kind of errors. What are those? So, first, generally 3 types of cameras generally we are using. First one is called the D-base carrier cameras, next one is called the back reflection focusing cameras, and the last one is called the pinhole diffractometers. So, when we are talking about the Hall D-base carrier cameras, for a Hall D-base carrier camera, the chief sources of error in theta are as the following, like film shrinkage, incorrect camera radius, off centering of specimen, and the absorption in specimen itself. So, first we are going to discuss about the film shrinkage and radius error. So, generally it is caused by producing and drying of the photographic film due to the temperature itself. Since only the back reflection region is suitable for precise measurements, the quantities S prime, phi and r are related as. In this particular case, you can see that this is the zone, it is known as S prime, and then this is r, and this angle is 2 phi and the 2 phi. So, here the incident beam is going like this, and then it is diffracted and it is coming through this, and this is S prime is the perimeter of that particular film where the diverted beam or maybe the diffracted beam is coming. So, phi is equal to S prime by 4 r, actually it is S prime by r is equal to 4 phi. So, logarithmic differentiation gives del phi by phi is equal to del S prime by S prime minus del r by r. So, in this particular case, the error in phi due to the shrinkage and radius error is del phi S prime due to the shrinkage and r due to the radius is equal to del S prime by S prime minus del r by r whole multiplied by the phi. The shrinkage error can be minimized by loading the film so that the incident beam enters through a hole in the film, since corresponding back reflection lines are then only a short distance apart on the film and their space separation S prime is little affected by the film shrinkage itself. So, in this particular case we are seeing that the incident beam is going in this directions and then it is diffracting and it is falling onto the film itself. So, if we are going to calculate the V value, so generally 2 pi minus 4 theta, which is nothing but this one. So, 2 pi minus 4 theta into the r, which is the radius, is equal to V. And in this particular case, when you are going to calculate this W value over there, so generally 2 theta by pi is equal to S by W, which is nothing by Stokes methods generally we are calculating. Next we are going to discuss about the off centering of specimen. So, an off center specimen also leads to an error in phi, that means we have to keep the sample in a particular locations. If the sample will be shifting, we can get some kind of off centering error of that particular specimen. So, any displacement of the specimen from the camera center can always be broken up into two components. One is del x parallel to the incident beam. If you see in this particular image that sample should be at the C prime locations, but now sample is around O. So, in between O to C prime is known as the del x in this particular case, and in this particular case in the B figure number B, sample should be in the C locations, but it has been vertically shifted to the P positions. So, here C prime to P is known as the del y. So, now what is the parallel displacement over there? So, error in S prime, this is the S prime over there. So, error in S prime is known as the AC plus dB, which is nothing but AC and dB is almost same. So, that is why 2 dB. 2 dB is nothing but the 2 ON if we put the perpendicular onto the C prime B line. So, if this angle is 2 phi, so automatically when will be your del x sin 2 phi. So, 2 into del x sin 2 phi is the parallel displacement in this particular case. And when you are talking about the right angle displacement, the effect of a specimen displacement at right angles to the incident beam is to shift the lines from A to C and from B to D. So, in this particular case you can see that A to C is also very near and B to D is also very near. So, del y is small, so automatically AC is almost equal to BD. So, to a good approximations, no error in S prime is introduced by a right angle displacement over there. So, in this case del S prime is almost is equal to 0. So, what is the total error? The total error in S prime due to specimen displacement in some direction inclined to the incident beam is therefore given by del S prime is equal to 2 del x sin 2 phi. So, from geometry of the camera we know that phi is equal to S prime by 4 r. So, in this particular case we are going to calculate both the errors actually. So, considering error in only S prime, we have del phi by phi is equal to del S prime by S prime. So, finally, the error in phi can be given as del phi c is equal to del phi s prime by s prime, which is nothing but is equal to phi into 2 del x sin 2 phi by 4 r phi is nothing but is equal to del x by r sin phi cos phi. So, this is the del phi c. So, next we are going to discuss about the absorptions in the specimen itself. So, absorptions it is also one kind of horizontal replacement type of error. So, absorption in the specimen also causes an error in phi. It is the largest single cause of error in parameter measurements and unfortunately very difficult to calculate with any accuracy. To a rough approximations, the effect of a centered highly absorbing specimens is the same as that of a non-absorbing specimens displaced from the camera center in parallel direction. So, it is reasonable to assume that the error in phi is only due to the absorption, phi del c is included in the centering error. Now, we are going to calculate the overall error by the Hall-Debeskerer cameras. The overall error in phi due to film shrinkage, radius error, centering error and the absorption is given by, here you can see that del phi s prime, that is the error due to the shrinkage, then r which is the radius error, c which is the centering error and absorption is a. So, del phi s prime r c a is equal to del s prime by s prime minus del r by r into phi plus means summation of the all the errors del x by r sin phi cos phi. So, from camera geometry we know phi is equal to 90 minus theta and del phi is equal to minus del theta. So, if we just simply change the order, so we can get this value over there and then sin phi is equal to cos theta and the cos phi is equal to sin theta. So, from Bragg's angle we know lambda is equal to 2 d sin theta. So, therefore, we have del d by d is equal to minus cos theta sin theta del theta is equal to sin phi by cos phi del phi, because cos theta we are replacing by the sin phi and then this sin theta we are replacing by the cos phi, that is why sin phi by cos phi in del phi. So, on substitutions, so what we are getting actually del d by d is equal to sin phi by cos phi into del s prime minus s minus del r by r into phi plus del x by r sin phi cos phi. So, in this particular case you can see that in the back reflection region if phi is small, whereas sin phi is almost is equal to phi and cos phi is almost is equal to 1, then del d by d will be del s prime by s prime minus del r by r plus del x by r into sin square phi. So, we are getting these equations in as a final, and then if we are going to make it more shorter, then del b by d is equal to k sin square phi, which is nothing but the is equal to k cos square theta. So, where k is nothing but the constant which is del s prime by s prime minus del r by r plus del x by r. So, k is the capital K is the constant over here. So, the important result is that the fractional errors in D are directly proportional to cos square theta and therefore approach 0 as cos square theta approaches 0 or as theta approaches to the 90 degree. So, in the cubic system, as we already know that del d by d is equal to del a by a is equal to a minus a 0 by a 0 is equal to which is nothing but the k cos square theta. So, a value is a 0 plus a 0 k cos square theta. So, hence for cubic substances if the values of a computed for each line on the pattern is plotted against cos square theta, a straight line should be result and a 0 and the true value of a can be found by extrapolating this line to cos square theta is equal to 0. So, this is also a one kind of conditions. Now, we are going to discuss about the back reflection focusing cameras. So, a camera of this kind is preferred over Hall-Debeskerer cameras for work of the highest precision. So, generally we are getting the better errorless results. So, since the positions of a diffraction line on the film is twice as sensitive to small changes in plane spacing with this camera as it is with a Hall-Davis scatter camera of the same diameter. So, in this case this is the film over there. So, generally the incident beam is coming through this line, this is the our sample. So, it is falling onto the sample and then back reflection is taking place and then it is coming in this point and this point onto the film itself. So, there are several types of sources like generally 4 types of systematic error for a camera of this kind is one is film shrinkage, one is incorrect camera radius, then third one is the displacement of specimen from camera circumference and last one is the absorption in specimen. So, what is pinhole cameras? The third one, the pinhole camera used in back reflection is not really an instrument of the high precision in the measurement of lattice parameters, but it has very great utility in work on highly textured on samples which cannot for whatever reasons be reduced to powder. Since both of the film and the specimen surface are flat, no focusing of the diffracted rays occurs and the result is that the diffraction lines are much broader than is normally desirable for precise measurements of their positions itself. So, in this particular case you can see that the incident beam is going and then some incident beam is reflecting and some incident beams are transmitted through. So, the chief sources of systematic error are the following: film shrinkage when photographic emulsions are used, incorrect specimen to film distance and third one is the absorption in the specimen itself. So, there are several types of errors when you are measuring the lattice parameter. So, in any physical observations 2 kinds of error are involved, one is called the systematic error, another one is called the random error. So, what is systematic error? Systematic error is one which varies in a regular manner with some particular parameter. Further, a systematic error is always of the same sign. Systematic error in A approach 0 as theta approaches to the 90 degree. So, almost in this particular figure we can get this one and may be eliminated by use of the proper extrapolation function over there. The magnitude of these errors is proportional to the slope of the extrapolation line and if these errors are small the line will be quite flat. So, in this particular case you can see that the points are nearly into the same place, there are not too much scattering over there, but when we are talking about the random errors are the ordinary chance errors involved in any direct observations which may be negative or may be the positive or maybe do not vary in any regular manner with the positions of the diffraction line. Random error in A also decreases in magnitude as theta increases due essentially to the slow variations of sin theta with theta at large angles and are responsible for the deviation on the various points from the extrapolation line. In this case you can see that the points are very far away to each other. So, now we are going to measure or maybe the methods, what are the methods to measure the error for lattice parameters. First one is called the Cohen's methods, second one is called the least square method and third one is called the calibration methods. So, when we are going to discuss about the Cohen's method, most accurate value of the lattice parameter of a cubic substance is found by plotting the value of A calculated for each reflection against a particular function which depends on the apparatus used and extrapolating to a value at A0 at theta is equal to 90 degree. There are 2 different things are accomplished by this procedure. What are those? First one is called the systematic errors are eliminated by selection of the proper extrapolation function, number 1 conditions. Number 2 is random errors are reduced using the least square methods devised by the Cohen. So, that is why it is known as the Cohen's method. So, generally for any cubic system that which being absorbed in a Hall-Davis scatter camera, del d by d is equal to del a by a is equal to capital K, which is nothing but the constant cos square theta as we have already gone through. So, in the Bragg's law lambda is equal to 2d sin theta. So, now we are going to squaring the Bragg's law and taking the logarithmic differentiation of each side produces del sin square theta by sin square theta is equal to minus 2 del d by d. So, substituting this into equation 1, the error in sin square theta varies with the theta as del sin square theta is equal to minus 2 k sin square theta cos square theta, which is nothing but is equal to d, which is a new constant sin square 2 theta. So, now the true value, so here is only the d is minus k. So, now the true value of sin square theta for any diffraction line is given by sin square theta true value is equal to lambda square by 4 a naught square into h square plus k square plus l square. So, if we substitute del sin square theta is equal to sin square theta observed minus sin square theta true is equal to sin square theta minus of this one. So, what we will get is equal to capital D sin square 2 theta. So, sin square theta is equal to lambda square by 4 a naught square into h square plus k square plus l square plus d sin square 2 theta. So, that means sin square theta is equal to c alpha plus a delta. So, where c is the lambda square by 4 a naught square, alpha is equal to h square plus k square plus l square, a is equal to d by 10 and delta is 10 sin square 2 theta. So, from the last equations we have got sin square theta is equal to c alpha plus a delta. So, the experimental values of sin square theta, alpha and delta are now substituted into above equations for each of the n back reflection lines used in the determination itself. This gives n equations in the unknown constants c and a, and these equations can be solved for the most probable values of c and a by the method of least squares, which I am going to discuss into the next slide. So, once c is found, a0 can be calculated directly from the relations, which is nothing but capital C is equal to lambda square by 4 a0 square. So, if we know the value of c, then automatically easily we can calculate the value of a. So, the constant a is related to the amount of systematic error involved and is constant for any one film, but varies slightly from one film to another. If lines from 3 different wavelengths copper k alpha 1, copper k alpha 2 and copper k beta are to be used in the analysis, the data must be normalized to any one wavelength by use of the proper multiplying factor. Now, we are going to discuss about the least square methods. So, in order to determine the lattice parameter more precisely, we should draw the best fit line through the experimental points in the plot and extrapolate to the point where the cos square theta is equal to 0 degree. So, these green in color all are the experimental data, and our calculated value we have plotted one line. The line should be like that it can satisfy all the points over there. So, let the coordinates of point x and y in the plot be related by the equations y is equal to a plus bx. So, to find the best fit straight line through all the x y points in the plot, we must find out the values of a and b. From equation value of y corresponding to x is equal to x1 will be a plus bx1. So, if the experimental value of y corresponding to that point is y1, then the error E1 for that point x1 y1 is given by E1 is equal to a plus bx1 minus y1. So, therefore, the sum of these squares, because now we have to add all this. So, errors in all the experimental points is given by summation over E square is equal to a plus bx1 minus y1 whole square plus for the x2 y2 and then up to it will continue up to xn yn. So, the theory of least square states that the best fit straight line is the one which makes the sum of squared errors a minimum. The best value of a is found by differentiating above equations with respect to a and then equating the result to 0. So, now we are differentiating with respect to a and then it should be is equal to 0. So, which gives summation over a plus b summation over x minus summation over y is equal to the 0. This is the number 1 equations, and then the best value of b can also be found out in the similar manner, like a summation over x plus b summation over x square minus summation over x y is equal to 0. This is our second equations. So, now rearranging the terms of equations 1 and 2, we can get summation over y is equal to summation over a plus b summation over x, which is nothing but summation over x y is equal to a summation over x plus b summation over x square. So, the above two equations can be used to get values of a and b for the best least square method. So, this is the number 3 and this is the number 4 equations. These two equations are the best fit for the least square method. So, now we are going to discuss about the calibration methods. The suggested procedure for determining the lattice parameters with high precision is, it should be carefully align the component parts of the instrument in accordance with the manufacturer's instructions. Adjust the specimen surface to coincide as closely as possible with the diffractometer axis, and the third one is that extrapolate the calculated parameters against cos square theta by sin theta or cos square theta to a value of theta is equal to 90 degree. Extrapolation should be done with least squares fitting of the data and the extrapolation function chosen to represent the systematic errors. So, now we have come to the end of this particular lecture and we have to summarize the whole lecture. So, in this particular lecture we have discussed about the different types of errors in systematic and the random errors which may occur in different cameras, methods and their respective remedies also we have discussed elaborately. Cohen's method we have used, which is nothing but the using the extrapolation functions, and the least square methods is used to get the highest precision in calculating the lattice parameter from the observed data. Thank you.